All right, let me show you the theorem and the corollary together. So we prove this theorem, and we use that theorem to get this version that it's the version we actually use. We have Wronskian. What is the conclusion about the independence and dependence? Is and this weird thing, there's this condition here that when you conclude the function is dependent, and here you need to know that the functions are actually coming from solutions of a differential equation. This Wronskian identically zero is not sufficient to conclude the dependency. So we'd like to give you an example where the Wronskian is identically zero, and we don't consider necessarily whether coming from zero or not, but it turns out this Wronskian is zero and it's not dependent, it's independent. From that example, we know this is a necessary condition to have. We need to have this condition to conclude, definitely to conclude that dependence. So the example is a 2x2 case, and you can of course use this example to go to the 3x3, but it's simple enough. So we have a function x squared and x times absolute value of x. Let me sketch this. You know x squared, and so I'm only going to sketch the function f2. So this is xy plane. So this is xy plane. So if x is greater than 0, absolute value of x is x. So and x is greater than 0, the x times absolute value of x is just x squared. Therefore, we have this usual part of the parabola showing up here. But when x is the same as 0 here, when x is less than 0, x times absolute value of x, this has to be negated so that x is negative, so this one becomes a positive number, so it's negative x squared. So the other one is actually part of the negative x squared. It looks like a lot like y equals x cubed, but the curvature is just quadratic, so it's never actually the same. This is a graph of absolute value of x times x in there. All right? And this absolute value of just x squared will be this usual parabola there. Now let's compute the Wronskian of these two functions. f1, f2 will be determinant of 2x2 matrix, where the first function is x squared and second function is x times absolute value of x. All right? So the second row is a derivative, so here's a 2x. If you differentiate it here, if you look at here y equals x squared, that's going to be always a 2x on that side, that's for sure. And on this side is actually the derivative, y prime in here, on that side is opposite. It's negative 2x in there. Okay? So if you sketch this one, this side 2x and that side a negative 2x. So the derivative of y dy dx in this case, this is something that you might have went through when you learned Calc 1, is that actually x and negative x put together as an absolute value of x. And you can show rigorously that derivative of x times absolute value of x is really 2 times absolute value of x, even for x equals 0 as well. So it is make sure that you understand at x equals 0, this function x times absolute value of x is differentiable. If you look at here, it's nicely connected. Of course, it's not second differentiable, but it's first time differentiable. So we have this 2 times absolute value of x as a derivative formula there. All right. If you compute the Wronskian over here, is a cross product is an x squared times absolute value of x minus 2 times x squared times absolute value of x. So that is identically 0. There's no matter what your x is, this turns out to be always a 0. Now it remains to show they're actually independent. The best method of doing that is looking at the column vectors, and the column vector v1 is plugging in the 0 in there. Well, I was wrong about this independence. This using the column vector idea uses the fact that all the functions arises from the equation of solutions, but we don't have that. Of course, if it is, and that is going to be dependent, and everything is wrong. So we have to use the very definition of independence, not using any tricks, right? Which is the following: to establish the independence, we have to consider this linear combination c1 times x squared plus c2 times x times absolute value of x being identically 0. And conclude that if this happens, c1 must be 0 and c2 must be 0. So if this is identically 0, you have to play with some special values of x and determine c1 and c2. So let's try x equals 1, for example. When x equals 1, this gives us c1 plus here's a c2 is 0. When let's try x equals negative 1, then that's going to be c1 again, and here's negative 1 picks up negative 1 and negative c2 and equals 0. And then c2, if you solve this equation, and it's always 0. So no matter what, if you try 2 points, it quickly picks up, all right, there's no choice that this 2 coefficient is necessarily 0. That's the proof of linear independence there. So let me show you the statement again. If you happen to have the Wronskian identically 0, and like this one in here, you can't just conclude from there is a dependence. There's this example that it turns out the functions are linearly independent. But if you have this additional condition, we can have definitely a conclusion that it's dependent. And so this is some important condition we need to put to conclude that it's dependency. But usually we use that in the context of a differential equation, so we don't think about this much. But this is a correct statement. I hope this is clear, the confusion about the conclusion for independence and dependence from the shape of the Wronskian there. Thanks.